Hi guys, in today's video it's a continuation of Manufacturing Systems Design Advanced PLC. In the previous video we were programming a virtual MPS station, a distributing station to be specific, using two simulation softwares, CIROS and Codesys. So I did give you a background of how our station looks like, what are our variables, what are the functions of our inputs and outputs. So in this video I will not go through that. I already also gave you a background on how to configure both our softwares. So we will configure our softwares because each and every time we program our virtual stations or robots, we need to configure both softwares. So everything that I've mentioned on the previous video is a repetition of it. The only difference is that in today's video, we will be programming this virtual station using a different coding language or a different programming language, which is a structured text. So in the previous video, we used ladder logic. In this video, we are using structured text. What is the difference between ladder logic and structured text? Everything is exactly the same, including the code. Why? Because we are using or programming the exact station. The only difference is that when you open your Codesys, you're gonna set a different language, which is structured text. You're gonna insert a different language or choose a different language, which is structured text. Number two, instead of developing or creating a ladder logic diagram, you're gonna have structured text. And it is very important for you to put everything in caps, because if your variables are in small letters in structured text, it will not read them. Okay, so those are the only two different things that we're going to introduce. So in ladder logic, when you introduce your timer, you insert what you call function blocks, right? But in structured text, we're going to be inserting a text instead of function blocks. But the difference is really minimum. So let us apply the knowledge that we already have from the previous video. You insert new project, but because our Codesys is usually slow to process, so we will start by configuring our CIROS. File, new MPS. So when you open CIROS, you're gonna have these two pop outs, or these two options. One is CIROS Education, the other is CIROS for educational purposes. So you're going to choose the one with gray area or with the gray sheet, and then file, new MPS. Student number, remember, initials, surname, choose a folder that will be easily identified by you, meaning that you'll use your student number, initial, surname for easy access when you are submitting both your files. So it's also important to save on DOS-space so that even if there's any computer malfunctions, you can retrieve your work. So you go to distributing conveyor, you add this because it's a continuation of our distributing station, just a different language. Close modeling, modeling explorer, under object, distributing conveyor station, PLC distribution, you right click, properties. Control, choose OPC client, and then under OPC client, items, connect. Choose virtual PLC bits and then apply. So we close this. It's time for us now to, okay, what happened? Okay, let me just start over. Hopefully I still have everything. Properties. Right, I've already chose OPC client, items, right. Connect, virtual PLC bits, then apply. You can close this. Okay, so our panel inputs are EP0s. You should know that by now. You should also know how to identify that. Then assign them properly, right? Our distributing inputs, they are EP1s. But always verify that by checking your code on Codesys. These are our sensors. Our ABs are AB1s. But then again, you have to double check that on Codesys. Because if you select the wrong bits, obviously your code will not run, or your station will not be properly programmed. And then you say, okay, just for interest's sake, let us check our code if our EBs and ABs, we've assigned them correctly. So we chose our panel inputs as EB zeros. What comes after X is 0, so we chose well. We chose our distributing inputs as EB1s. What comes after X is 1. We chose our distributing outputs as AB1s. What comes after X is 1. So this is the best way of identifying what you have to choose on CIROS when you are choosing your code, or when you are configuring your code accordingly. So that's fine. We have applied, and then from there you can close. Then you can play around with your station if you want to see. You want to see how it looks like. Zoom in, zoom out, rotate, just to get ready to simulate your station. From here, restart, play, insert your components. So if you're going to start with Codesys, there's nothing wrong with that. If you start with CIROS, there's also nothing wrong with that. Standard project, student number, initials, surname, save under a folder that you can access. And then the language, you choose structured text instead of ladder logic. And then the device, Codesys control, WinV3, okay. From there, online simulation, application, right click, add object symbol configuration, ensure support OPC UA features is enabled as well as optimize layout, then click add. From there, go to settings, you enable direct IO access, and then what's left is for you to build. I don't like to build before inserting my code, because then I'll only have 2 symbols or options to enable. I might then forget to enable also my PLC PRG. Go to your code, you copy, and then paste it between your var, which is variables, and end variables. From there, that's when we can build. So it's okay, it's perfectly okay if you're going to start building and enable only these 2 options. Thereafter, inserting your code, you come back and enable your code as well. There's also absolutely nothing wrong with that. So usually in ladder logic, this is where we're going to be having our coils and contacts, creating our ladder logic diagram. So because it's structured text, we're going to be inserting our structured text. But the same process applies. What are we programming at distributing station? What do we want it? How do we want to run it? We want the push button to actuate or to enable our acting cylinder to advance. So we're going to say if, everything must be in caps, if PO, which is our push button, then Q4, which is our acting cylinder extent, should be true. And underscore if. So if the start button is activated, then our acting cylinder should advance. That's what this means. Okay. Once our cylinder is advanced, remember it is doing what? It is supplying items onto the conveyor belt. So once it gets to the conveyor belt, sensor I1 needs to activate our conveyor belt. So if I1, then conveyor belt equals to true, it must start running, and if. Right. So remember, our inputs or actuators that initiate or actuate the process, in ladder logic, we created a latch to send a continuous signal to keep on extending our conveyor belt, right? And then we also did the same with our conveyor belt. We had our sensor, which is I1, that was activating the conveyor belt to start running. And then what opposed the process is I2, which stops the conveyor belt from running once a part is detected by the sensor. So these inputs that are opposing the process, we're also going to insert them in structured text. So if I5, then Q4 should be, so if I5, what is the purpose of I5? I5 is a sensor that detects a fully advanced position of a cylinder in order for it to send a signal to the cylinder to retract to its initial resting position. So what is the current state of I5? It is normally open. Hence, in ladder logic, we negated, changing its state to become normally closed so that current can flow, right? In order for us to achieve our output, which is the acting cylinder to advance and to latch, right? So now we are saying if I5 is activated, then will Q4 be true? Will Q4 be true? No, it will not be true. It will be false. Why? Because the state of the sensor is open, meaning there's no current that will be flowing. Therefore, the acting cylinder will retract instead of advancing. So our acting cylinder will semicolon. Okay, then what's opposing our conveyor belt is I2. I2 is a normally, our I2 is always on, meaning it's a normally closed, right? So in ladder logic, we don't negate I2 because already current is flowing. So meaning that when activated, it cuts power. It stops the current from flowing, right? Because when a part gets to I2, then the conveyor stops. So our conveyor, which is Q0, if I2 is activated, then Q0 will not be true but false. However, okay, so let us start with this. Right. However, what is the state of our I2? Our I2 is normally closed, right? Meaning that current flows until it detects a part and it cuts power. So if I2 is activated, then Q0 is false. It's not false. Q0 will remain true when I2 is activated because it's normally closed. So in order for us to change its state in structured text, we need to say if I2 is not activated, then Q0 will be false. Right. Okay, and then what else? What is our other input that opposes our process? It is P1 and it's our common input because we have it in both processes, which is for the conveyor as well as for the cylinder. So if P1 is activated, then Q0 equals to false because it opposes the process. Q4 is also equals to false. And if, okay, from here we are done. We have our process. So when we run our code, we're supposed to have our cylinder advancing and then the conveyor belt moving forward. Don't forget to build, log in with download, play. If there's something wrong with your code, this will be disconnected. This will be disconnected, which is your Codesys will be disconnected. Your virtual controller will be disconnected. Usually if you have a S7 PLC SIM controller by default, there you go, it's disconnected, execution suspended, one client is connected, which that's correct. So usually you'll get your Easy OPC connected to S7 PLC SIM controller by default, right? So you have to change that and click Codesys controller because you have your CIROS connected virtually to your Codesys. Then you're going to have your installed Codesys connected to localhost, virtual controller connected, one client connected. If your version is version 2, go to Codesys, settings, choose the correct version. Then go back to overview, minimize. This is giving you a green light that your configuration is correct and you can now simulate. Have we pressed play? Okay, we did. So we can now simulate. Okay, let us restart, play, insert our items, then start our process. Okay, is this connected? Yes, it is. Let's go back to our Codesys and check if we have configured properly. Simulation, enabled I/O. Did we build? Yes, we did. Okay, is there anything that we didn't introduce? No. We have everything. We play. Then our code should run. If it doesn't run, then there's probably something wrong with our structured text. Okay, log out, stop, log out. If you see these blue lines, you can just click your space button on your keyboard and then they'll disappear. Right, let us check our code. If P0 is activated, then our acting cylinder should advance. If I1 is activated, then our conveyor belt should run. If I5 is activated, then our cylinder should retract, right? Meaning that it shouldn't advance since it's written false, so it must do the opposite, which is retracting. If not, if I2 is not activated, then our conveyor belt should stop, right? It should stop, hence written false. If P1 is activated, then Q0 should be false. So what is the current state of our P1, which is our emergency switch? It is normally closed, meaning that current flows, right? So if P1 is activated, our Q0 would be true and not false, right? Because its current state is closed. So in order for us to ensure that if P1, right, is activated, then Q0 should be false, is by changing its state from being a normally closed. So we need to say if not P1, then Q0 equals to false. These two are normally closed, so the same method applies under P1 since it also opposes the current process of your program. So from here you build, and then our circuit, or rather our station should run. Okay, let us check our station. Restart, play. Did we click play? No, we didn't. Now it should run. Acting cylinder advances, release the part to the conveyor, and then retract. Once the part gets to I2, then the conveyor belt stops. So we have achieved exactly what we wanted. We can just try it one more time. Great. Restart. Okay, so now we're going to introduce a timer. For our acting cylinder. Okay, so our acting cylinder, we're going to introduce a timer. Our I5. So we're going to say if I5, then M0. Remember, M0 is what? Is your latch, your memory latch, right? So we replace I5, even in our ladder logic diagram, with a memory latch whenever we set a timer for that input. We replace that input with a memory latch. So when we inserted a 5 seconds delay for the retraction of our cylinder, then we replaced our I5 with MO. So that's what this code means. If I5, then it needs to execute a memory latch, which is MO. And if, never mind the red lines, it means you have introduced a new code and you need to declare. So you can declare immediately or you can declare after. It's still okay. When you declare, please check the type here. So for your memory latch, those are booleans, so you select bool. But for your timer, you need to select TON, which is ton. right? So we have declared. To check if indeed you've declared, you can just go at the bottom of your code, and there you go. You have indeed declared. So if you like, you can just type this instead of clicking that light bulb. You'll still achieve the same results. So if I5 is activated, then it needs to memorize a memory latch that is written or introduced as MO. It should be true. I5 should be true once it memorizes the delay, the timer delay. Then now it's time for us to introduce that timer. So we say timer underscore 1, and then you open your bracket. Its input equals to MO, because MO is what is replacing our input. So our input equals MO, and then PT, which is your processing time, you insert the seconds. So it's T hash 5 seconds, and then you close your bracket, then semicolon. Okay, so we can go back and go to your timer, click the light bulb. Here it's written Intel. So if you say okay, you would be declaring an incorrect timer. So you need to insert TAN. When you check the options, TAN is not here, so you just need to type it by yourself. Then you've declared. So this PT, you also have it. Remember, your timer is represented as a function block in ladder logic, and you insert your 5 seconds or the seconds that you want the timer to memorize or the input to memorize. So you represent it exactly the same way. It's TH and then the seconds and then S for the units. Okay, and then remember for your first line, second and third, we were inserting end if because that's the end of our code. But for a timer, we have a semicolon here because it's not the end of our code, or rather we are defining our timer and we are not yet done. So it continues, hence the semicolon. And then as it continues, we're giving our output a new variable, which is M1. So we say M1 equals to timer underscore 1 dot Q. Because remember, in ladder logic, your contact when you insert a timer, the first thing is your input, right? Which is connected to your set function block. From there, you declare that set function block, and then you insert your timer. Then you declare it, and under PT, which is your processing time, you insert TH and the number of seconds that you want to delay your process with. And then what connects to your timer is then now your output. So this M1 equals to timer underscore 1 dot Q represents your output. So in as much as your timer is a function, you represent them in function blocks, this is how you represent your timers in structured text. So from here, we then need to, you need to insert your semicolon again because you are not done. Now you need to introduce your M1 in your code or program. So if M1, right, then Q4 if M1 and then so if M1 then Q4 is true, and if M1, remember we are setting a timer for our I5 to delay the retraction of the cylinder by 5 seconds, right? So when we insert, meaning this is our output for our timer, this is the memory that has already been inserted in our input. If our I5 memorizes this memory latch, which is M0, then our Q4 cannot be true because our Q4 is advancing a cylinder, but now the timer is not for advancing the cylinder but for retracting. So then we need to insert false. Why? We are retracting, and our Q4 is for advancing. Okay, right, so we end if. And then what opposes now our processes? So we have P1, which opposes both processes, the conveyor as well as the acting cylinder. And then we need to then also introduce our timer, because it also opposes our timer, our M1 as well as our M0. And then end if. Right. Okay, so it's red because we haven't declared. It's our boolean. That's correct. Okay, so if not I2, I've already explained that, then Q0 is equals to false. And then what are we missing? Are we missing I5? Okay, so we have our PO, I5, which is true, and then we have our if not I2, and then if not P1. So this is the end of our code. Let us run it. Before we run it though, we need to build. Okay, let us pay attention one more time to our code. If the start button is activated, then the cylinder should advance. If sensor number 1, I1, is activated, our conveyor should run. If sensor number 5 or I5 is activated, then it should recall a memory latch, which is MO, given by timer _1 input MO PT delaying by 5 seconds. This should give us an outcome of M1. Then we introduced our M1. If M1, then Q4 is false. So if our I5 is able to memorize the delay from MO, then our acting cylinder should retract. Hence, if M1, then Q4 equals to false. And then if not I2, then Q0 is false. If not P1, then QO is false, and so on and so forth. So did we build? Let us build. Log in with download, okay. And then play. So if it's still red, your stop is red, then it means you haven't selected play or press play. Once you press play, it's gonna turn green, giving you a green light to simulate your MPS station on CIROS. Restart, play, insert your part, and then play. Our cylinder is taking 5 seconds to retract. There we go. Okay, so I can just show you both screens, but unfortunately our CIROS, I don't think it does a countdown in structured text, but we know in ladder logic it does a countdown. Okay, so let us see if it will do a countdown. Reset, play, insert our part. Then let us, did we click play? We did. Did we? Okay. Okay, let me stop, restart, play. Okay, then our cylinder should take 5 seconds to retract. There we go. So yes, indeed, our Codesys doesn't count down, but at least it's visible that the acting cylinder indeed took, executed or memorized the 5-second delay. Okay, so from here, stop, you log out. And then we're going to introduce a delay now for our conveyor belt to start running after 10 seconds. Or let us just change our cylinder to retract after 10 seconds and then add a delay of 5 seconds before our conveyor belt starts running. So what initiates the what stimulates the conveyor belt? We have our I1, which detects a part when placed on the conveyor belt and then sends signals to the conveyor belt to start running. So our I1, we are now introducing a new memory latch, which is going to be our M2, right? And then this memory latch, we're now going to give it a timer. So instead of our timer being timer_1, now it's going to be timer_2, because it's a second timer. You're introducing another timer. It's not, you are not using the same timer. And then your memory, it's still going to be 2 because that's your input, right? And then your processing time, how long do you want to delay? You want to delay by 5 seconds. So T hash 5 seconds, close, don't forget a semicolon. Then what do we have to introduce now? It's our output, the output of the timer. So which is, we're going to say that's our M3. I'm going to say M3 equals to timer underscore 2.q. Then don't forget a semicolon. Right. Okay, let us check our M3 timer underscore 2.2. That's it. We've introduced our timer. It's time for us to introduce the memory latch in our code. So if memory 3, then what are we delaying? The conveyor belt from running. So then Q0 should be true. And if. Okay. And if. So we're having these red lines because we haven't declared. We haven't declared. Declare. Your timers, don't forget when you declare. Okay, so your timer is done. Okay, your M3, is it declared? Okay, if you can't see your boolean, or it's already declared and it's wrong because it's a boolean, and okay, we correct that. If M3, then Q0 equals 2, we forgot equals 2. Here's the thing about structured text, you forget one small thing, you become wrong. Semicolon. Right, so we've declared everything and we should be good to go. Okay, let us just observe the rest. We forgot because since we introduced a new timer, we need to insert our M2 equals to false, M3 equals to false. Then don't forget to end your code. Great, so from here, build, enable your code, PLC, log in, we download, don't forget to play, and then there's no need for me to show both Codesys and CIROS because it doesn't count down. So from here you can just stop your machine, restart, play, insert your parts, and then start. So our conveyor belt will run after 5 seconds and then our cylinder will retract after 10 seconds. Okay, we're waiting for our cylinder to retract. There we go. You can just repeat the same process again to observe if really your station is programmed exactly how you want it to. 5 seconds, the conveyor will run. After 10 seconds, the cylinder will retract. There we go. So that's the end of our lesson, guys. That's how you program your distributing station using structured text as your coding or programming language. So one tip I can give you, make sure that you really go back to your code, check if it makes sense. It really does program your robot how it's supposed to, and everything should work perfectly fine after that. Okay guys, thank you. That's the end of our lesson. All the best with your test next week. Bye.